Directions in hexagonal systems. We're going to use the three-axis system consisting of the unit vectors HKL. Consider the unit cell of the hexagonal system. Along three of the edges, let's define a unit vector called H. Relative to H, going counterclockwise, we have a unit vector along another edge of the cell. Let's call that K. And then perpendicular to the plane containing H and K, let's define a unit vector L. These are the three unit vectors that make up the three-axis system. Let's put this in the context of the hexagonal arrangement by adding additional lattice points. Let's see how we can use these three unit vectors to express any direction drawn within the hexagonal system. Let's see how we can represent this direction, shown by the green arrow, as a combination of the vectors h, k, and l. That is the aim of finding the Miller indices of any direction. So, how can we create this vector through a combination of these three? Well, we see that if we take the k vector and add that to the h vector, we'll end up with a translation that is equivalent to our green arrow. So from this, we can define the h, k, and l indices as being, for the h direction, we are going one unit. In the k direction, we traverse 1 unit, and in the l direction, we traverse 0 units. In that way, the indices of the direction shown by the green arrow are given by 1, 1, 0 in the three-axis HKL system. Let's do another example. Let's see how we can represent the vector shown, again in green, but this time going from a different starting point to a different ending point. Let's see how we can represent that vector in terms of, or that direction, in terms of h, k, and l. And to help us with this task, I've also drawn vectors that represent the negative of h, k, and l. Starting at the tail end of the direction, we realize that we must go down in the opposite direction of the L vector, and then once we've reached this vertex here, if we go along the K direction, we should get to our destination. So we can see that we must combine 0 h with plus 1k and minus 1 L. I'm not sure how to put a bar on this software, so I'll just leave it at that. But we should write that 0, 1, 1 bar. Now it turns out that if we just use the HKL Miller indices to describe directions in the hexagonal system, then directions that are crystallographically similar do not appear similar when just using the three-axis system, the HKL. And so the Miller-Bravais system was devised, which has 4 axes. H as before, K as before, but now we have an I direction known as a redundant direction because it is a combination of H and K, and we have the L direction as before. To convert between the two, we use this set of equations. If H prime, K prime and L prime are the Miller indices in the three-axis system, then H, K, I, L are the Miller-Bravais indices in the four-axis system. To convert, we can use these equations, and let me just give an example. Let me take, let's have a look at this 100 direction as an example. So if I say that H prime equals 1, K prime equals 0, and L prime equals 0, then H will be equal to 1/3, 2 times 1, minus K, which is 0, 2 times 1, so that's going to be 2/3. The K is going to be 1/3, 2 times K, which is 0, minus H, so that's going to be minus 1/3. The I is going to be minus 1/3 H plus K. H plus K is 1. That's going to be minus 1/3. And finally, the L is simply equal to L prime, which is 0. We have 2/3 minus 1/3 minus 1/3, 0. When we clear fractions, by multiplying by 3, we see that the 1, 0, 0 direction is equivalent to 2, 1 bar, 1 bar, 0 as shown. The next thing we want to learn how to do is how to index planes in the hexagonal systems. In order to do this, we will use the H, K, I, L coordinate system. And the first thing we will do is to find the intercepts of the plane with the H, K, I, L axes. If the plane intercepts with the origin of our coordinate system, we'll have to move our origin. Let's have a look at the plane which I have outlined with my blue pen and see how we get this result. This is the H, the A1, this is K, and A3 is I, and of course we have the L direction going upwards in the along the z-axis. What are the intercepts in the H on the H-axis? We can see the plane is cutting the H-axis at 1. So this is our origin, and we see it cuts it right here at 1. It doesn't cut the k-axis at all, or it will cut it at infinity because it's parallel to the k-axis. And it cuts the I-axis at -1, and it cuts the L-axis at 1 unit. So we have the intercepts, and now as before we calculate the reciprocals. 1, 0, -1, 1. So the plane, the answer is the plane, the Miller-Bravais indices of the plane are 1, 0, 1 bar, 1. So we've shown how to get the indicated result. The general properties of planes that we might be interested in are planar density, the number of atoms intersected per unit area, whether they are close packed or not, and something of interest for identifying crystals is to know the interplanar distance. This is the perpendicular distance between adjacent planes. And in a cubic system, the interplanar distance is given by this formulae, which is equal to